When there is a problem with a neutral conductor in a direct buried cable, several methods can be employed to locate the cable and identify the fault. Firstly, ground-penetrating radar, or GPR, emits high-frequency radio waves into the ground and analyzes the reflected signals. This technology can detect buried cables, pipes, and other objects by identifying anomalies in the subsurface. Secondly, cable locators are instruments designed to induce a signal into the conductor, which creates a magnetic field that can be detected by the locator. There are different types of cable locators. One type is tone generators. Tone generators emit a continuous tone that is picked up by the receiver. Another type is pulse induction locators. Pulse induction locators send out short pulses of energy. And another type is radio frequency locators. Radio frequency locators use higher frequencies for greater accuracy. Thirdly, thermal imaging detects temperature differences in the ground caused by buried cables carrying current. It is important to know that thermal imaging can only locate cables that are actively carrying a load. Fourthly, step fault locators inject small pulses of current into the neutral conductor at regular intervals. When a fault occurs, such as a break in the neutral, a sharp increase in voltage is detected. Step fault locators require access to the neutral conductor at both ends of the circuit. Fifthly, electromagnetic field, or EMF, detectors detect electromagnetic fields generated by buried cables. EMF detectors can be used to trace the path of cables or locate faults. Sixthly, visual inspection involves examining the surface of the ground for signs of disturbed soil or discoloration. It may also involve digging small test pits to expose and trace the cable. In addition to these methods, consider these tips. Firstly, check construction plans or site maps for cable locations. These documents can provide valuable information about the cable's route and depth. Secondly, use multiple methods to cross-reference findings. Combining different techniques can improve the accuracy of the cable location. Thirdly, be aware of the depth and burial method of the cables. Knowing how the cables were installed can help in selecting the appropriate detection method. If you are not comfortable performing these tasks, contact a qualified electrician for assistance. Working with electrical systems can be dangerous, and it is important to take proper safety precautions. When using ground-penetrating radar, the device emits radio waves into the ground. The reflected signals are analyzed to create an image of what is beneath the surface. Different materials and objects reflect the radio waves differently, allowing the operator to identify potential targets such as buried cables. GPR works best in dry, sandy soils. Clay soils can attenuate the signal, reducing the effective depth. Cable locators work by inducing a signal into the target cable. This signal creates a magnetic field around the cable, which can then be detected by the locator's receiver. The locator typically consists of two parts, the transmitter and the receiver. The transmitter is connected to the cable and generates a signal. The receiver is used to trace the magnetic field and pinpoint the location of the cable. Tone generators are a simple type of cable locator. The tone generator emits a distinct tone that can be easily identified by the receiver. Pulse induction locators send out short pulses of energy. These pulses create a magnetic field that is detected by the receiver. Pulse induction locators are generally more accurate than tone generators. Radio frequency locators use higher frequencies. They are more accurate, but they can be more difficult to use. Thermal imaging cameras detect infrared radiation, which is emitted by objects based on their temperature. Buried cables that are carrying current will generate heat, which can be detected by the thermal imaging camera. Thermal imaging is most effective when the cable is carrying a significant load. The greater the load, the more heat the cable will generate. Step fault locators work by injecting a small current into the neutral conductor. The current flows through the conductor until it reaches a fault. At the fault, the current will take a different path, creating a voltage drop. This step fault locator measures the voltage drop to pinpoint the location of the fault. Step fault locators require access to the neutral conductor at both ends of the circuit. This can be a challenge in some cases. EMF detectors detect electromagnetic fields generated by electrical currents. Buried cables carrying current will generate an electromagnetic field. The EMF detector can be used to trace the path of the cable or locate faults. EMF detectors are relatively simple to use, but they are not as accurate as some of the other methods. Visual inspection involves carefully examining the ground for signs of disturbance. This can include things like discolored soil, sunken areas, or patches of dead vegetation. If a cable has been recently buried, the soil may be looser and more easily disturbed. Digging small test pits can help to confirm the location of the cable. However, it is important to dig carefully to avoid damaging the cable. Before digging, always call 111 to have underground utilities located. This will help to prevent accidental damage to buried cables or other utilities. When using any of these methods, it is important to follow all safety precautions. Electrical cables can be dangerous, and it is important to take steps to protect yourself from electrical shock. Always wear appropriate personal protective equipment such as gloves and safety glasses. Be aware of the potential hazards associated with each method. Work with a qualified electrician if needed. They can help you locate the cable and repair the fault safely and effectively. The 2008 National Electrical Code, or NEC, provides guidelines for the safe installation and maintenance of electrical systems. Article 300.5 covers underground installations. This section specifies the minimum burial depths for different types of cables and conductors. For example, direct buried cables are typically required to be buried at least 24 inches deep in residential areas. The NEC also requires that underground cables be protected from physical damage. This can be achieved by using rigid metal conduit, intermediate metal conduit, or rigid non-metallic conduit. The specific type of protection required will depend on the location and the type of cable. The NEC also includes requirements for grounding and bonding of underground cables. Grounding helps to protect against electrical shock. Bonding helps to reduce the risk of fire. Always follow the requirements of the NEC and any applicable local codes when working with electrical systems. Ignoring these requirements can create a dangerous situation. In addition to the methods discussed above, there are also some specialized tools and techniques that can be used to locate direct buried cables. One such tool is a cable fault locator. This device sends a signal down the cable and then measures the reflected signal. By analyzing the reflected signal, the cable fault locator can pinpoint the location of the fault. Another technique is to use a tracer wire. A tracer wire is a non-energized wire that is buried alongside the cable. The tracer wire can then be located using a cable locator. Tracer wires are often used when burying non-metallic cables, such as fiber optic cables. When troubleshooting a neutral problem in a direct buried cable, it is important to start by identifying the symptoms. Common symptoms include flickering lights, appliances that do not work properly, and tripped circuit breakers. Once you have identified the symptoms, you can begin to troubleshoot the problem. Start by checking the voltage at the outlets and appliances that are affected. If the voltage is low or erratic, this could indicate a problem with the neutral conductor. Next, check the connections at the service panel and at any junction boxes. Make sure that all of the connections are tight and corrosion-free. If you find any loose or corroded connections, clean them and tighten them. If the problem persists, you may need to use a cable locator to trace the neutral conductor. Look for any signs of damage to the cable, such as cuts, nicks, or abrasions. If you find any damage, repair or replace the cable. If you are not comfortable performing these tasks, contact a qualified electrician for assistance. Working with electrical systems can be dangerous. Only qualified personnel should perform electrical work. When locating direct buried cables, it is important to be aware of the potential hazards. These hazards include electrical shock, explosions, and damage to other underground utilities. Take all necessary precautions to protect yourself and others from these hazards. Always wear appropriate personal protective equipment, such as gloves, safety glasses, and hearing protection. Be aware of the location of other underground utilities, such as gas lines, water lines, and sewer lines. Call 811 before you dig to have these utilities located. Never dig directly over a buried cable or utility line. Dig around the cable or line carefully. If you damage a buried cable or utility line, immediately evacuate the area and call the appropriate authorities. The process of locating direct buried cables, especially when there's a neutral issue, involves a systematic approach using a combination of technology and careful observation. Firstly, understanding the site conditions is crucial. This includes reviewing any available documentation such as site maps or construction plans, which may indicate the approximate location of buried utilities. The depth and type of soil can also affect the performance of certain locating methods. Secondly, visual inspection plays a role. Look for any surface indicators such as utility markers, pedestals, or signs of recent excavation. These clues can provide initial guidance. Thirdly, ground-penetrating radar is a non-destructive method that uses radio waves to create an image of the subsurface. The GPR unit transmits radio waves into the ground, and the signals reflected back are analyzed to identify buried objects, including cables. GPR is effective in various soil types, but its performance can be affected by factors such as soil moisture and conductivity. The interpretation of GPR data requires expertise, and it's important to have a trained operator analyze the results. Fourthly, cable locators are designed to detect the electromagnetic field produced by a cable carrying an electrical current. The cable locator typically consists of a transmitter and a receiver. The transmitter is connected to the cable, either directly or indirectly, to induce a signal. The receiver is then used to trace the path of the cable by detecting the electromagnetic field. There are different types of cable locators. Tone generators are basic locators that emit a continuous tone signal. Pulse induction locators send out short pulses of energy to energize the cable. Radio frequency locators use higher frequency signals for increased accuracy and range. Fifthly, thermal imaging can be useful in detecting cables that are actively carrying a load. Thermal cameras detect infrared radiation, which is emitted by objects based on their temperature. Cables carrying current will generate heat, which can be detected by the thermal camera. Sixthly, step voltage measurement involves injecting a small current into the ground and measuring the voltage gradient around the suspected fault location. This method is particularly useful for locating ground faults in buried cables. Step voltage measurements require specialized equipment and expertise. Seventhly, tracer wires are often buried alongside underground cables to facilitate locating. The tracer wire is a conductive wire that can be energized and traced using a cable locator. This is a proactive measure taken during cable installation to simplify future locating efforts. Eighthly, direct excavation or potholing may be necessary to visually confirm the location and condition of the cable. This should be done carefully and with appropriate safety precautions to avoid damaging the cable. Ninthly, when a neutral issue is suspected, it's important to perform electrical testing to verify the problem. This may involve measuring voltage, current, and resistance to isolate the fault. Tenthly, after the cable has been located and the fault identified, repairs or replacements can be made. This should be done by qualified personnel in accordance with applicable codes and standards. 11thly, documentation is key to preventing future issues. Detailed records of cable locations, depths, and any repairs made should be maintained for future reference. In addition, ongoing maintenance and inspections can help to identify potential problems before they become major issues.